I want to show you two numbers, 60 tokens a second and 167 tokens a second on same graphics card, same model file, same prompt, same quality of output, absolutely identical, token for token. I know what you're thinking. Maybe different quantization, different hardware. Something was traded away, but nothing was traded away. No new hardware, no smaller quant, no quality given up anywhere. One flag did all of it, and that flag already shipped inside the model file sitting on your desk right now. It's called MTP, multi-token prediction. And in almost every tool that people are using to run this model, it is off. Not broken, not missing, just off. Qwen released these weights on August 14th with an MTP head trained in. The speed is free. Nothing extra to download. Nothing traded away. And surprisingly, the output is identical. And the number in your terminal is probably nowhere near it. I found this out in the most embarrassing way possible, by spending 3 days convinced I had it configured correctly, watching my terminal report a perfectly reasonable 70 tokens per second, and then discovering that a single word in my config had gone stale 3 months before this model even existed. The setting was accepted. It was running. It was doing absolutely nothing. So in this video, I want to explain what MTP actually is, why it's off everywhere, where the traps are, and how to actually turn it on depending on which runtime you're using. But before we touch the flag, I need to explain the problem it solves. Because once you understand the bottleneck, the solution becomes obvious. Generating text is a queue with one server, one token at a time. One full pass through 27 billion parameters, and then start over for the next word. And here's the thing that surprised me when I first understood it. That pass is not limited by arithmetic. It's limited by memory. Your GPU spends most of every pass dragging weights across a memory bus so it can multiply each one exactly once. Each token generation is basically the GPU reading 18 gigabytes of model weights to produce one single word, then reading the same 18 gigabytes again for the next word, then again, then again. A card doing 80 tokens a second is not thinking 80 times. It is reading the same 18 gigabytes off memory 80 times in a row for 80 single words. The math is fast. The memory is the bottleneck. The GPU is mostly waiting. This is why MTP matters. Not because it makes the GPU faster, because it attacks the waste instead of the work. So let's understand what MTP does, and if I have to explain it in 2 words, it's speculative decoding, which is what MTP is doing under the hood, is one of those ideas that sounds complicated, but is actually elegant once you see it. Here's the concept. Something cheap and fast guesses the next few tokens ahead. Then the real model checks all of them in one pass, for roughly what a single token used to cost on its own. If the guesser was right, 4 tokens arrive for the price of 1. If the guesser was wrong, the bad tokens get thrown out and you land exactly where you started. A wrong guess costs you anything. It cannot cost you anything else. That's the key insight. The full model verifies every drafted token before it ships, so speculation is incapable of changing the answer. The quality guarantee is mathematical, not hopeful. By switching this on costs you nothing in quality, ever, under any circumstances. The normal version of speculative decoding requires a second model, a smaller, faster drafter that you have to find, download, and keep resident in memory alongside the main model. That's usually a few gigabytes of extra overhead and a configuration headache. Qwen trained the draft head directly into the model file instead. It's already there. Ollama has 12 tags live for this model, and 3 of them are marked MTP. The 4-bit tag weighs 18 gigabytes with the MTP head and 18 gigabytes without. It adds essentially nothing to the download. The speculator is built in. One gotcha before any of this works, and I'm flagging this early because I got burned by it. Qwen 3.8 27B is a dense model, not a mixture of experts model, dense. Which means the flag that half the internet reaches for, the one that pushes experts onto the CPU, does absolutely nothing here. There are no experts to push. The right configuration is plain layer offload plus the speculative flag. Here's the embarrassing part, the part I promised to tell you. And I'm telling it because I believe this is why most people's terminals are showing the slow number. On the 13th of May, 2026, 3 months before this model existed, the llama.cpp project changed how the speculative decoding flag is spelled. Multi-token prediction itself landed in the main branch 3 days after that rename. The old spelling was not removed with an error. It's still accepted. It just gets quietly ignored. Generation keeps running. Speculation simply stops. Your throughput collapses. Your command line still reads correct. And nothing in the log gives you any reason to look. One write-up measured the damage on a 4090, about 140 tokens a second, falling back to about 70. Half the throughput gone from a setting you're certain you configured, because one word inside it went stale. And every guide written before that Wednesday, every tutorial, every Reddit post, every YouTube video from before mid-May still carries the dead spelling. You can be completely certain you've done it right and be completely wrong. I was, for 3 days, watching 70 tokens a second like it was fine. When I finally found the correct spelling, updated the flag, and restarted the server, the number jumped. And I had the specific experience of feeling both happy and deeply annoyed at the same time, which I think anyone who has debugged a configuration problem for 3 days will recognize. Fix the word. Switch it on. The rest is a dial. The flag doesn't just have an on position. It takes a number. How many tokens to guess ahead? On the day this model shipped, a developer swept that number from 2 all the way up to 8 on a Blackwell workstation card and published the whole acceptance curve. At 2 guesses ahead, 81% of drafted token sequences survived the verification check. At 5, 56%. At 8, 40%. Guess deeper, and you're wrong more often, exactly what anyone would predict. But here's what's strange. Throughput refuses to follow acceptance down. It climbs to 115 tokens per second at 5 steps, then falls back. There is a peak in the middle of the curve, not at the beginning. Most recipes published online set this to 2 or 3, which leaves as much as 27% of available throughput on the table. The number the community copies is not the number the hardware wants. And then a second researcher found something stranger still. His draft acceptance had collapsed from around 85% on the previous model release to around 65% on this one. Nothing had changed in his setup. Same hardware, same config, same runtime. The cause turned out to have nothing to do with the model at all. It was temperature. He was running the sampler at 1, because that's what Qwen's own authors recommend for this model. A hotter sampler flattens the probability distribution over the next token, which makes the draft head's guesses wrong more often, because the full model is picking from a more spread out distribution that the drafter can't predict as reliably. He swept temperature downward and watched acceptance climb. Draft accuracy went up. Speed went up. So the setting that decides your throughput is not the throughput setting. It's the temperature setting, 3 lines earlier in your config. And it puts a real choice in front of you. Do you follow the model author's recommended temperature and accept lower draft acceptance, or do you turn it down to buy throughput? Neither answer is wrong, but you need to know the choice exists. Now here's what this actually looks like across different hardware, because the same flag produces wildly different results depending on what you're running it on. NVIDIA 3090 and 4090, the most common setup. The numbers here vary dramatically by task. One reporter measured 167 tokens per second on agent turns and 93 on standard prompts on the same card with the same file. Same flag, same everything. Nearly double, decided only by what you ask the model to do. Agent turns have shorter context and more predictable structure, so the drafter does better. That's why the single number in any benchmark is almost always a ceiling someone measured with the conditions cropped off the end. One important limit for 3090 and 4090 owners. You will see headline numbers like 206 tokens per second showing up for this model. That number belongs to a 4-bit format called NVFP4. It exists. It's real. And it only runs on Blackwell Silicon, the RTX 5090 generation. The tensor cores that run NVFP4 natively are not on the 3090 and 4090 die. That number is not slower on your card. It is unreachable. AMD's own release day post quotes up to 51.8 tokens per second on a workstation Radeon, and every figure in it was measured on Vulkan, not ROCm. Not on the stack AMD builds, staffs, and markets. Independent testing puts Vulkan 20 to 30% ahead on generation for these cards, with ROCm ahead on prompt processing. A vendor publishing its own launch numbers on somebody else's backend says more about driver maturity than any blog post ever could. The real trade on AMD is memory. A 16 gigabyte Radeon owner posted both sides of it. At 128,000 tokens of context, 32 tokens per second. At half the context with the flag on, 51. Nearly 60% more speed, bought with half the context window. The download is free. The memory is not. Apple Silicon. Someone benchmarked a 48 gigabyte laptop and went from 8.3 tokens per second at 8-bit to 20.3 with a ported drafter. 2.45 times on average, 3 times at peak. But here's what's better than the multiplier. 8-bit with drafting beat, 4-bit without it. 20 tokens per second against 14.6. better answers and more speed in one run. Quantization never usually offers you that trade. It's usually quality versus speed. The MTP head flips the equation. One desktop Apple owner reported the biggest jump in any of these threads. 10 tokens per second on llama.cpp, up to 70 on a Metal engine with handwritten kernels for this architecture. The flag didn't do that, the kernels did, but the point stands. On Apple, the stack you're running on matters as much as the flag. The machine where it buys you nothing. A 12GB laptop owner published both runs. 4-bit with the flag on, 4.5 tokens per second. 2-bit with the flag off, 12.8 tokens per second. 2.8 times faster from the crude thing the clever thing was meant to replace. His model didn't fit on the card. Part of it was offloading to system RAM over PCIe. Speculative decoding hides memory latency by keeping the GPU busy while data loads. It cannot hide a transfer that hasn't started yet. On a machine where the bottleneck is the cable to system memory, the flag does nothing. Worse than nothing, because you're paying the overhead of running the drafter with no benefit. The lesson is straightforward. Buy your video memory for the quantization, not for the flag. Multi-token prediction multiplies the speed you already have. It cannot create speed that doesn't exist. Now let's talk about how you can actually set it up. Currently, 4 runtimes support this. 4 of them spell it differently. None of them ship it on by default. Here's the map. llama.cpp. Look for speculative ngPQ layers in the spec type flag. Make sure you have a build from after May 13th, 2026. That's the rename date. If your build is older, the old spelling is silently accepted and does nothing. Rebuild from source if you're not sure. vLLM, the speculative config hides inside a JSON blob nested in the serving configuration. Look for the speculative decoding section of the vLLM docs specifically for the version you're running. It's not a command line flag, it's a config key. sglang, it's listed as the speculative algorithm parameter. sglang published 206 tokens per second on an RTX 5090 on release day, but remember, that figure uses NVFP4, which only runs on Blackwell. The flag itself is available on older cards, just with lower ceiling numbers. Ollama, you don't set a flag at all. You pull a different tag. The tags marked MTP are the ones with the draft head included. Pull one of those 3 tags instead of the default, and you're done. This is actually the cleanest setup of the 4, no config editing required. One thing to check regardless of runtime. Start your draft depth at 4 or 5, not 2. Community recipes copy 2 because that's what early tutorials used. The throughput curve peaks higher than that on most hardware. Test it yourself and find your card's peak because it will be different depending on your specific GPU and the tasks you're running. So the flag shipped. The capability is real. The quality guarantee is mathematical. Wrong guesses get thrown out. The full model verifies everything. You cannot get a worse answer from turning this on, only a faster one. The reason it's still off in most terminals is not that it's obscure, it's shipped. The instructions rotted. A rename happened in May, and every guide written before that Wednesday still carries the dead spelling. Accepted, running, doing nothing. Fix the word. Pull the MTP tag if you're on Ollama. Check your draft depth. And if your model doesn't fit on your card, skip all of this and buy more VRAM first, because this multiplies speed you already have. It doesn't create speed from nothing. The 3 numbers that live in my head after going through all of this. 81% acceptance at depth, 2 versus 40% at depth 8, but throughput peaking somewhere in the middle. One card showing 60, 93, and 167 off the same file, decided only by the task. And a laptop where the flag off and the crude quant beat the flag on and the smart quant by nearly 3 to 1. Every figure in this video is true. Every one of them is a ceiling someone measured with the conditions cropped off the end. Your number will be different. Run the sweep. Find your peak. If this saved you the 3 days I lost on a stale flag, hit the like button. Subscribe for more of this kind of breakdown. And drop a comment with what you're running and what numbers you got after turning this on. I'm curious whether people are seeing the same variance by task that the benchmarks suggest. See you in the next.